much thanks to the invitation. It's a great pleasure to be here. So my plan for lectures is here today. I want to tell you a little bit about local theory because that will be important in understanding intrinsic mirror symmetry, which I will tell you about tomorrow, and I will tell you how to calculate explicit equations of mirrors following some work I did. And on the third lecture, I will talk about our previous joint work with macros, which is a higher dimensional tropical vertex, and finally I will talk a little bit about mirror symmetry and classifiers. Okay, so to start with low-chromatic theory, this is a theory developed by Abramovich, Chan, and Gross-Siebert. Just to give a naive picture, this is a generalization of relative chromatic theory of Chini, in which you're interested in counting curves, but you're counting curves with respect to some tangency conditions, with respect to the divisor, which is not necessarily smooth. So our interest is to count curves in this space X, which satisfy some tangency conditions. And I will tell you how do we define stable log maps. I will give you the definition and set up the counting problem. So to define the counting problem, to define such log maps, I need to talk about log structures, which will enable you to tell how to describe contact orders with respect to the divisor D using some sheaves. So I will tell you the definition of a log structure on a scheme X. It's given by the data of a sheaf of monoids, which I will denote by mx and leave it as a multiplicative monoid together with a number of multiplicative monoids, a morphism of monoids that we denote by alpha to the structured sheaf, such that the restriction of alpha on the invertible elements is an isomorphism. So you have an isomorphism from alpha inverse OX star to OX star is an isomorphism. The definition looks pretty ad hoc, but I will give you a couple of examples to illustrate this. One thing to remember, there are two parts of such a structure, one discrete part which is easier to understand and one torso part in a log structure. So the discrete or tropical part is the part of the log structure where we do use this condition such that when you restrict to the invertible elements to get an isomorphism, you can just look at the sheaf of monoids and get rid of the invertible elements, and then what you get is what we usually call the ghost sheaf, which encodes all the data, all the tropical information, defined as the quotient of mx by this isomorphic copy of OX star inside it. And then you have a torso part or non-discrete part of a log structure, which you can define by looking at the map, the natural quotient map from your sheaf to your ghost sheaf obtained by quotienting out this isomorphic copy. And if you take any section of your ghost sheaf, if you let U over n opposite U, then kappa inverse U is an OU star torso. And what we will often do when you do low-chromatic theory is we will start with setting up the problem tropically, which we will describe maps using these ghost sheaves. I will tell you how this is used to define tropicalizations and turn the problem into lifting maps on ghost sheaf levels to torso levels. Okay, so let me give you some examples on how we do that. Let's explain how it goes. log structure, a trivial log structure. So often I will suppress the notation alpha from my notation and define the nodal log scheme just by x and x, because often we will know what alpha should be. So the trivial log structure is simply given by taking the invertible elements, and then alpha will simply be the inclusion to your structure sheet. So on any scheme, you can take the trivial log structure by taking your mx to be just Ox star. So as an example, if you take the point spec C together with C star, you will call this the trivial log point. Of course, there's also another natural log structure you can take. You can take just x together with Ox and define the map identity, but that will not be a nice log structure. For instance, if you quotient out, if you look at the Gauss shift, that will not be nice, so we rather prefer this one. Okay, so there can be many different log structures, and I will tell you in a minute another log structure just on the point. So I will obtain from the divisorial log structure, so whenever you have a divisor, an x in a scheme, and let me denote the complement of this divisor included in x by the inclusion map J. Then there is a natural divisorial log structure you can define, which we often use. So you can take your mxt that I will denote my sheaf of monoids for the divisorial log structure. You can take the sheaf of regular functions on x. You can look at all regular functions which are invertible away from D. So this is a sheaf of all regular functions on x invertible away from D. And again, there's a natural alphas given again by the natural inclusion into Lx. So this is what we call the divisorial log structure. So if you look at A1 together with the divisor 0, if you let the coordinates on A1 to be equal to t, if you look at the sheaf of all regular functions on A1, so if you look at the Gauss sheaf at an arbitrary point, so h times t to n, so where h is an invertible function. So if you look at the stock of your log structure, it will be generated by all such functions, an invertible function times t to n, a regular function. And if you look at the stock at such a point x of your Gauss sheaf, rather than your log structure, around a point x, you simply just forget about the invertible function. And similarly to the log map, you can just remember the order n. So this you can define an isomorphism mapping t to n to n, which will tell you that your stock of your log structure will be isomorphic to the natural numbers at any point away from the origin. Sorry, this is at the origin, because t to n will be invertible away from the origin. Because t to n will be invertible away from the origin, if you quotient out by the invertible elements, you will have nothing left. So away from the origin, x will be just trivial, simply because t will be invertible away from the origin. So your stock of your Gauss sheaf here over the origin will be n, and everywhere else it will be 0. If you look at the regular functions on A1 invertible away from 0, your Gauss sheaf will just have a non-trivial stock of a 0, and everywhere else it will be trivial. Is that okay? a log scheme, one way to describe the tropicalization is to look at the complex given by, using the Gauss sheaf, so the tropicalization trop, which is the motion depending on what log structure you use, is a union of cones of you define for every scheme theoretic point the union of cones from m bar at this point to r greater or equal 0. And then you need to glue these cones together. For that you use some generalization and specialization maps to glue them together. So in this example, only from the point 0, your Gauss sheaf is non-trivial, and only from there you will get a copy home and are greater than or equal to 0, which will give you a copy of r greater or equal to 0. And in this case, the tropicalization of A1 with the student-oriented log structure is just going to look like a copy of r greater or equal to 0. And you can see whenever you consider a toric variety, and if you take the toric boundary divisor in your tropicalization, you will see a cone structure similar to the one of your toric form. You will obtain essentially your toric form. If you additionally consider an affine structure, integral affine structure in your tropicalization. Okay, so do you ask me questions at any point? The nice thing about log structures is you can pull them back. I don't think you have any questions about. So you can, whenever you have a log scheme, if you have a scheme theoretic morphism, y to this, x, if you have a morphism, if you have a scheme theoretic morphism, if your target is a log scheme, if you have a log structure here, this induces a pullback log structure here. So there's a natural way to define this pullback log structure, because whenever you have such a scheme theoretic morphism, you have a natural map f inverse x to f inverse ox to oy between your scheme theoretic map between the structure sheaves, and then you have a natural map f inverse x to f inverse ox, because you have a log structure here, you have this map alpha, and you obtain this by composite with f inverse. Hence, whenever you have a scheme theoretic map to a log scheme, you already have morphism of monoids, that we call this beta, from some monoid to your structure sheaf. So this is what we call a pre-log structure, because whenever you have a morphism to your structure sheaf, this is what we call a pre-log structure. If in addition your morphism satisfies that it restricts to an isomorphism on invertible elements, this would be a log structure. And here it doesn't necessarily satisfy that condition, but there's a natural way to make it satisfy the condition that we want an isomorphism once restricted to the invertible elements. So to have that, you can define a natural log structure by taking this monoid, take the direct sum with OY star, take the forward coproduct of a beta inverse OY star. And then, if you define your map to OY just by taking the economy here, mapping it to beta of A times B, then you can check this is a log structure, and let me call this alpha. Then you can check by property of fiber products. Alpha restricted to the invertible elements will be an isomorphism. So to any pre-log structure, whenever you have a log structure, there's a pre-log structure, there's a way to turn it into a log structure by using some fiber products. And this construction allows you to define the pullback log structure whenever you have backup schemes to a log scheme. So, morphismal schemes, and the target is a log scheme. And if you consider the targets, if you, for instance, look at A1, if you consider the divisorial log structure by taking the device as 0, where we set the only non-trivial stalk of your Gauss sheaf will be over 0. And then you can wonder what happens if I restrict this divisorial log structure to 0, if I look at this point, spec C, corresponding to 0, and if I pull back the divisorial log structure, then what you get is the log structure on this point, which is given by C star. If you follow this construction, you will get your log structure obtained by pulling back this divisorial log structure given by this monad, sheaf of monads. And you will have a natural map to Ohm spec C, which is C, mapping any R, N to either R or 0 if N is 0 and 0 if N is not equal to 0. So that it will be an isomorphism on the invertible element C star. So one can check if you do this construction of pullback log structure, if you restrict your divisorial log structure to this point, you will no more get just the trivial log structure, but your log structure will change. This is what we call the standard log point, not the trivial log point. Okay, so there can be many log structures depending on what you want. If you look at another higher dimensional base, you can get other monoids.
But they are all, is it always C star as the one?
Yes, as long as you have a coherent log structure, so whenever you work, for instance, with a toric variety, just restrict to a point. So it will always be like that. For instance, whenever you work with a toric variety, spec C, Q, if you assume that you have a nice monoid such that Q star is 0, then you have a single fixed point. And at a single fixed point, your pullback log structure, so if you look at the toric divisorial log structure on the toric variety, if you assume this condition, there is a unique fixed point, you can show this will imply that there is a unique toric fixed point. And if you restrict, you will get spec C and Q direct sum C star. And it is true that this will always be sum and to some other. It could be more complicated depending on the toric variety. It's not always not if you have, it doesn't always necessarily need to be coherent. Okay, depending on your toric variety, this is not always, okay. Of course, if you always take AM, it will be answer. So if you take,
Singular.
but you can have singular toric varieties. If you take an n-dimensional affine space, then this will be giving that n2r, but it doesn't need to be an you can have singular toric varieties. Okay, if your toric variety is an, then you always get okay, so now you defined these two different log structures. At least I can tell you what kind of things are we going to look at. So in log harmonic theory, to start with, the target is a log scheme with a log structure, and similarly to in harmonic theory, we want to work with a base, but in log harmonic theory, we want to work with some base which also has a log structure. And I want this to be a log point, the base. And depending on what is the context that I'm interested, where I'm interested in pointing curves, we will choose different log points. So there are usually two natural situations where we are interested in pointing curves. We call them absolute.
You're not assuming fx is a full
Yes. No, I don't assume. I don't assume M is the pullback of MW, so at this point it can be anything. But to define my mass marginalized spaces, I will put some assumptions. So the absolute case, and I can have the relative case. So we're usually interested in doing harmonic theory in two different situations. In the absolute case, we just get one single target piece. We pick something ISO, and we're interested in counting curves with respect to T. And in this case, we usually just consider the divisorial log structure of the target. And in this case, we take the again will be just a trivial log function. You can define a log structure in arbitrary generality on any not necessarily reduced scheme. But yes, and it could be a non-reduced toric variety. We can still take the to be the normal for some toric.
You want me to assume that things are log source?
Yeah, so, okay, so if you can still define a marginalized space of log maps and define log structures, everything, without assuming X to be reduced or anything beyond this. But to show that, to prove that you get a linear matrix like from your marginalized space, you will need to assume it is reduced and is not as log sort. So you will need to put assumption. So you don't need to assume log sort to define the virtual class to be log sort. So, okay, so to get a linear matrix like I will assume that X is reduced. And I will assume this map, I will put assumptions while doing harmonic theory. I will assume this map is projected to get a proper modularized space. I will assume it is also going to get a virtual harmonic class. I will assume X is reduced to get a and generally you can define log structures arbitrarily, but it won't be good modularized spaces. So the relative case is usually what we call also the degeneration situation. In the relative case, what you do is you're looking at the one-parameter degeneration, so your x can break into pieces, and you're interested in counting curves in this degeneration. And so in this case, if you look at one-parameter degenerations, if you want to understand low curves here, which are obtained by smoothing low curves in the central fiber, then you need to choose a different log structure. Then if you look at the one-parameter degeneration, you will consider W and W to be standard. So depending on where your interest is in counting curves, you decide what to take for your log point. So if you're interested in counting curves only in some spaces, in absolute situation, you can just set it to your log point. Okay. What time did I start? I have half an hour. Okay, perfect. Okay, so let me define what is a stable log map. A stable log map is a commutative table where I look at my domain curve is a marked nodal curve. Other ones, if you forget the log structures, I want a stable map. So MC. So if you forget the log structures, there's a usual notion of a stable map ensuring that automorphisms of your curve, which is a marked nodal curve, will commute with F. But here I know everything with log structures, and I do know already my target is always some log point. And I also want my domain to be over a log point. And you call this map pi. And I want a commutative diagram. And I want to put a condition on this map pi such that
So S and W is some log point.
they're all log points, yes. So this is a log point I already described depending on the situation. If you're in absolute or relative, you know what to take to W and W. And this is a log point also. So this is given by some monoid Q plus C star. Generally, like we discussed, the monoid, it doesn't necessarily need to be NR, depending on. But it's always a monoid Q because I always work with the complex numbers.
Is this fixed or is this dependent on
This, yes, for any given F, you have a Q. And in a minute, I will tell you if F is good to consider into our homogenized space or homogenized space or not, depending on if this Q is good enough or not. So if I don't put any assumptions on Q, if I just look at all possible such maps without any assumption on Q, the homogenized space will be not possible to control. But I will tell in a minute what this Q should be. So it just depends on that. For every F you have a Q at this point. So I want pi to be log split. And the underlying map which I will denote by this is stable in the usual sense that automorphisms of the domain commuting with F is finite.
So this is bounds.
give you the intuition, maybe let me just recall. Assume you're in the nice situation that Q star is just trivial, then as you said in the toric variety spec C, Q, there's a unique fixed point. And on this unique fixed point, you get this log structure, spec C, Q directs C star, which is SMS. If you pull back the divisorial log structure on the toric variety, so in the toric variety there's a natural divisorial log structure where you take the toric boundary device and you pull it back to the fixed point, you get this. And what does it mean to be log smooth? A log smooth curve is typically a curve which you should think of arising as a degenerate limit of a family of curves over the toric variety. So a log smooth curve, C is log smooth. I will not tell you the complicated technical definition, but you should think of it as the degenerate limit of a family of curves over the toric variety. So C is, there's the family of generically smooth curves over the toric variety such that in the degenerate limit with C, the degenerate limit. What I mean is C can be smooth over this base given by the toric variety. For instance, if you look at base A1, an ordered curve given locally by the equation xy equals t is going to be log smooth. So maybe it's just so if you look at the model curve in the total space, if you have this equation xy equals t, this curve is log smooth over the divisorial log structure, over the point which you impose a log structure by pulling back to the divisorial log structure on A1.
Dependent on MC.
Yes, it depends on MC. A10. So if you consider the divisorial log structure here, so this point will have log structure spec C and direct some C star. So such another curve will be log smooth over this point, which geometrically you can think of, you can smooth it in Bachmann into family.
So MC is the whole one.
Yes, maybe the right thing. MC is not, it's not a pullback from the base, but it is a restriction from the natural divisor log section of the total space.
To that curve.
Yeah, to that curve. You should draw the
Oh,
other curves.
you're asking what is MC on this
Yeah,
curve?
exactly.
I'm sorry, I was right. Okay, yeah. So MC is not obtained by pulling back here, but on the total space of this family of curves, there's the divisorial log structure as Felix said. If you restrict that log structure, you get MC. And maybe I should mention there's this nice result of Hülya ARGÜZ, which characterizes all local nature of log structures that can appear on log structures.
So this case is also a gauge tube is also true, it's like
Over here, at this point, at the model point, the gauge sheaf is not trivial. So over any point away from here, the gauge sheaf is up, which is coming from the base. At this point, it is, if you have also markings, at the markings it is n squared, and at this point it's a little bit more complicated depending on what is really your local equation looking like. If this is say t to a, it will be, okay, so
in the simplest case.
in the simplest case, if this is t, it is n squared. So to describe the local nature, like Hülya ARGÜZ describes all like local M bar C at any scheme theoretic point X. He classifies so that this needs to be log smooth. And one way to understand this classification that I often deduce how it should be, like I look at if you have like a curve C with two components, say these marked points, a stable curve, you can look at the tropicalization of the dual graph and then put it at height 1 and then take the clone over, if this is at height 1, if you take the clone over the strata, so every vertex here corresponds to a point of the tropicalization. If you look at the column connecting the origin to this vertex, then the integral points here will give you n. And that n is exactly the both sheaf at smooth points on your curve, which will always be this Q. Over marked points correspond to lags, so you will get a copy of n squared. One n will come from here, and the other n will come from leaving this point as a resort as a local. And over nodes, you will get the integral points of the monoids you obtain by taking the convoluts, and it constantly, your local equation, if you would have an n here, you would take something of a finite and unfathomable Gromov equation. But if it is just t, you will get an exponent or something. Okay. That's the definition of a stable block map. And you can ask the question, what if I consider a modular problem? If you want to define a nice modular space, you need to put restrictions on this point on this monoid Q. So to define those restrictions, what we usually do in our Gromov theory is we fix something called the type. So we define a modular space of all stable block maps of a given type, and the description of type will tell you what to take to Q. So what is Q? Where shall we take Q to get a nice modular problem? To do this, I need to define the notion of the type of a stable block. The type of a stable block map is the data of 4 things. The first thing is the data of the dual graph of C, dual graph, which I denote by gamma of C. So as I mentioned, here you're just replacing every irreducible component by a vertex. I will denote a set of vertices by V gamma. They correspond to irreducible components of C. I denote a set of edges by E gamma. They correspond to nodes of C. And I will denote by L gamma a set of legs. And they will correspond to marked points. Okay. So I want to encode the data of the dual graph. And the second thing I want to remember, I want to fix, when talking about the modular space of block maps is the genus. So I will fix the genus map. Zero. So if you have any vertex, I know that it corresponds to an irreducible component. Let me denote by CV the corresponding irreducible component to the vertex V. And this map just sums the vertex to the genus of CV. And the third thing I want to fix is a map sigma. So I want to find is also called just tropical time. So this is a map from the union of vertices and edges and legs to the tropicalization of your target, which sums any either vertex or edge or leg to the palm of MR f of x. So assume x is a scheme theoretic point corresponding to either vertex or edge or leg. If you have a vertex, x will be a generic point of the irreducible component. If you have an edge, x will just be not corresponding to that edge. If you have a marked point, if you have a leg, it will be just a marked point. And this is a cone. So this gives you a cone inside the tropicalization, which is the union of all complexes of the scheme theoretic points. So what we say is we fix the log strata every scheme theoretic points maps to. And finally, the last thing we fix is all contact orders at marked points and nodes. So we also want to fix the data of all contact orders at special points. So these two give you more information than just fixing the contact orders in addition to we fix the strata. Like, for instance, if you have x, if you have a divisor, say like this, and if you want to look at curves which intersect this point, which intersect intersection of divisors at contact order 1, say, it could look like this, or it could look like this. So we want to specify by telling what exactly it looks like. So we don't only specify the contact order, but we want to specify the strata, like saying I want to look at curves with contact order 1, with respect to the divisor of the union of T1 and T2. It's not enough to tell where your marked point goes, but we want to specify where our marked point goes. Okay, so this is the definition of insight. And one can check this definition. I will not talk much about tropical curves, but this description of type tau that we denote specifies what we call a tropical time. If you look at the tropicalization f trop of your curve c trop, which will be gamma the dual graph to the tropicalization of x and x, which amounts to specifying essentially the data of like contact orders will specify the waves on your tropical curve at all edges, and you specify the data of which leg and edge goes to which strata in your tropicalizations. So once you have the data of a type, you can check.
So when you say gamma, what is this? The vertex?
This is like the dual graph of C.
Yeah, but it's not really mapping. Are you mapping the whole graph, or is this mapping the vertex and edges and this?
Right, so
Yeah, when you take trop, you don't get the
I get some family of tropical curves, right. But if I
the general fiber is gamma.
yes, the general fiber is gamma. Let me say trop C. Thank you. Right, but to this question,
It's about the
yes.
full graph. Yeah.
it's a full graph. Like if your S is the trivial log point, you will get gamma. If S is not the trivial log point, you will get the family of curves. So because if S is not the trivial generally see, because even by definition of tropicalization, if you tropicalize, you will, whenever you have the C and C to X and X, there is this commutativity over S and S. So if you tropicalize, even from these points, you get the Loschief's M. So if you tropicalize, if you don't take the trivial point, but if you take this direct sum C star, so if you tropicalize this, you will get the pawn over the dual graph. Generally. But the tropicalization of this will also be r greater or equal to 0, and then you need to restrict to some natural. By the commutativity, there will be some natural height functions which will allow you still to describe, if you restrict at a given height, the map from gamma to the tropicalization. But there's some. Okay, if you assume you have the trivial one point, that will just be gamma. It will define the whole map, the tropicalization. Okay, so. Once we have you can check if you look at the motional space and tau space of all tropical curves of type tau. So I didn't tell you what a tropical curve is, but it's like a balanced, weighted balanced graph where you have a metric balancing condition. Weighted directions add up to 0 in the image around every vertex. One can check that. So this is a cone. And you can define Q tau, the moment of integral points in this cone. There's some very yes. Okay, so this cone will be like Q greater or equal to 0, which is Q tau. And due to some general effects about bourgeois spaces of tropical curves, this satisfies the universal property. So there exists morphism from home Q to r greater or equal to 0 with r basic point for the stable map to home Q tau to r greater or equal to 0.
It should also be Q tau.
For any tau. So in particular, we have by universal property of tropical modular spaces a natural map from Q tau to Q, if you take the loops. Right. Okay, so this exists by general tropical geometry that I didn't talk much about, but by universal property of tropical modular spaces. Q tau. So yes, this was the Q in the stable base and the stable log map. And now we define the stable log map F from this V says there's this natural commutative diagram over this S MS, so Q was here. Basic if this is an isomorphism. Q tau is isomorphic to 2. Okay, and this MS was Q direct, so when we look at stable log maps, we fix their type to be the natural type so that we can get universal properties of modular spaces. And then, only once you do that, if you look at the modular space of all basic stable log maps, this will give you a nice modular space. they showed that this marginalized space is a linear matrix set.
What does O do?
It's the genus of the domain. And furthermore, if you assume that this right-hand side map that is denoted by H, if H is projective, then this marginalized space is proper.
Maybe they do amplify that?
Yeah. Yeah, so you should not fix.
Yeah, the tower.
Yeah, you should look at all the towers specialized with these fixed towers. So yeah, you should fix a
there's
tower.
some technical subtlety, okay.
So you should look, once there's a long arc of tau prime, so the tau prime cannot retract to the tau.
Sometimes off-type tau prime, such that tau prime retracts into tau. Otherwise, you won't get anything from
So it's like having some explosion.
You're right. And finally, if you assume H is log smooth, they show that you can construct a virtual fundamental class. And once you have a virtual fundamental class, you just have to find numbers out of it by integrating. Similarly to, I will finish. How many? 3 minutes or something? Okay, perfect. I will finish in 3 minutes on time. Maybe I will just say a couple of words. So once you have this, so this uses a natural log generalization of semi-stable reduction theorem, and once you have this, you can define low-probability invariants. Numbers. Similarly, in probability theory, you can fix cohomology insertions in your cohomology of X. You can look at evaluation maps from your marginalized space to X and integrate over the virtual fundamental class the product of these evaluation maps. Put back. However, actually, this is you can define it this way to obtain numbers. Once you have this virtual fundamental class, similarly to as a usual probability theory, you can get numbers by looking at. This is not quite what we do usually, because there are a lot of subtleties here. Because if you fix arbitrary insertions, arbitrary cohomology classes, you're not going to get evaluation maps which are non-stop maps, so you need to do something. So it's a subtle, so you usually need to extend your target to get nice evaluation maps. So there's the whole story of Abramovich et al. To define evaluation spaces. But you can forget about the evaluation maps and define a virtual fundamental class to encode the information of where your function need to go. So, okay, so let me just give one example and finish in a minute. A very, very old example, though, just to illustrate Abramovich Bertram. If you look at F2, if you fix your genus to be 0, your class to be 2C2, where C2 is the curve and the usable surface F2 is self-intersection 2. If you fix 7 points in general position, if you look at the marginalized space of homogeneous zero curves through 7 general points of this class, you will get a probability number. All curves, so these are general points through VI. Then you will get a probability number which is 12. This will be a usual probability problem. But if you impose an addition, in addition to these, if you impose that you want your curve tangent at the toric boundary and tangent at boundary F2 at 8 points with contact order 1. Then you get a log chromometer number, which is 10. Yes, so the contact order is just order of tangency. We do define this using log structures, so
Yeah, that's why it's difficult to show.
we're not tangents. So the discrepancy arises because there are two of the curves which behave like 10 of the curves behave generically like this, but two of the curves will have components that map into here, and then they behave like this. So there's a very old paper, before anything about low-chromatic material was developed, the paper is called, its title is The Formula 12 equals 10 plus 1 times 2. And they explain why is this discrepancy generally rising, and they explain why is it a nice thing to do low-chromatic material. Because in a lot more situations, low-chromatic material is enumerative, in a lot more situations than usual chromatic theory, low chromatic theory is actually more accessible, it's more enumerative, you don't need to worry about virtual stuff, for instance, in a lot more situations. Like in all toric varieties, you get name comes, you can get name comes in low chromatic theory, but it shows you that it's enumerative. So it's a lot more, in a lot more situations you can easily define low chromatic theories. Okay, I think I ran out of time, but I'll stop here if you have any questions. Right, so that's a good question. So let me think of some example. Maybe I can construct a model here.
Some very trivial
Like
example.
Okay.
The most trivial example, we can X is a trivial log structure, and then C to be a smooth curve. Then to be basic, you need to do the trivial log structure of the smooth curve.
Yeah, so if you take spec C star, the trivial log structure, then the only curves that are basic are smooth curves. You cannot have any singularities. C is smooth. So a curve with any singularity cannot be basic of the trivial log point, because to be basic means if you have some C star direct sum Q, it means basic curves over such a thing can have singularities, and they will smooth in a family of this dimension. So, like if Q is okay, but
yeah, so for example, yeah, single node. Yeah, it's not smooth. It's not log smooth over the trivial log point. It's not smooth over that.
but he was asking basic.
X in one is basic, but you could try if you put something bigger than n, it will not be basic.
Okay,
Like
so
you could always add some trivial copy. You could add on the base like n to the power 10. You just put back the
it will still be log smooth, but not
yeah,
basic.
but not basic.
So I think the good way to think of, so this is log smooth and basic over this, but if you increase this over this, it will still be log smooth but not basic.
So basic is kind of the minimal and universal way to get something.
yes, but because well, in any case, when it's a log curve, this is the data come with F.
Yeah.
That's true,
Right.
yes. You determine
So
by
so basically the basic one is the only one that you can choose.
Yeah, that's
Yeah.
Otherwise, we just keep on adding.
Yeah, exactly.
Yeah.
And then the
So-
resistance
so
is
you
got
can-
to be bounded.
Why do you just put the basic as part of the definition? Just require the basic.
Yeah, it's a terminology.
It's true. It's going to be
There's no
very
follow up
specific
for
for
not allowing basic.
Exactly. So,
So yeah, only for finding the definition of basic because it's a bit development because the naive thing you want. It is the wrong thing.
yeah, that's true. So basic, a map is basic first if it's smooth over the base, but it's the minimum thing where it's smooth over and that the universal property is satisfied. So you can think if you take arbitrary Q, you can arbitrarily extend it, so you know if you don't put any basicness assumption, you never get a finite type moduli space. So basicness is a natural notion so that you get a finite type moduli space. And
But also the thing is, you may not have, but it does just similar.
that's true. Yes. Yeah, they should have put it inside the definition, so it's just a number.
I didn't hear what you said about the cycle thing. What was the cycle?
Right, so I said, like in probability theory, what you do is, I mean, there, you can define invariance once you have a virtual fundamental class by fixing cohomology insertions and taking evaluation map, pullback of these insertions, and taking the product to get down numbers. Abramovich et al. Showed that if you take arbitrary insertions, the evaluation maps are not nice block maps. So there's some technical subtlety.
Yeah, I think you could always do the naive thing and the right thing. But if you want some like compatibility with not choice, then you train with that.
Because you said you define the number.
Okay, definitely these numbers are defined. But for example, maybe these numbers are not enough. Maybe you need more numbers.
You need more numbers.
Yeah, maybe you want more numbers.
Yeah. So you can
Why?
they show that I never really read the paper and it's never really published. It's about expanding your target X into an evaluation space so that you can define more compatible evaluation maps
Yeah,
to
that's
get
nice.
more numbers.
Yeah.
How do you enlarge?
Yeah.
What's the synthesis?
Yeah, I think you just yes, the evaluation space is some kind of you replace X by some like stucky version of X.
What's the simplest case? Let's say
Yeah, so if you just have let's say P1 and you have a point, and if your my point goes to the divisor, then instead of doing evaluation at this point, maybe you want evaluation to the stack point or GM.
But when you don't have GM, you where's the GM?
Yeah, intuitively sometimes GM is in the normal direction of the divisor.
Oh,
Yeah, in the case of a smooth divisor, it has some interpretation as a more classical system. Psi class,
Like, this is a story that in Abramovich invariance of, in the recent papers of Abramovich, Grossi-But et al., they never really want to fiddle with the subtlety.
Yeah,
So they, to not worry about the subtlety, they rather change the definition of moduli space, and they already include the data of variance. So they look at the moduli space of this type of class beta into X, and they also say of, they look at maps passing through already the conditions. So they put the data of this inside the moduli problem, and then they can show you can construct a virtual fundamental class by not of this moduli space, but already imposing the data here in some way.
without changing X, you changing the definition.
Rather than worrying about this, they change the definition of the moduli space because this is subtle.
so if you only want to define some numbers, you can do it in the naive way.
Yeah.
But if you want to have properties like some kind of gluing axiom, like saying 2 points can go to the same point and you will pull back the class in diagonal two sets, 2 points come together. Then if you work with these naive things, this property will not work. So this thing matters if you want to set up a proper like cutting and gluing formalism. Then you need to run kind of more type of exceptions.
But this is around the D.
Yeah, that's right. Exactly.
If we generated the P1 along the accessory.
Yeah, that's okay.
Is this something similar to what the sign classes?
Yeah, it's a bit, yeah. But I think convergent is not. Yeah, it's like in Julian language, you will generate the target.
Yeah.
And then you like to look at convergent classes on the generate target instead of exploration.
Like,
In your case, it's also some of the code can sit completely inside.
Yeah, that's right. Yeah, that's right.
right.